Here are some examples of one-step syntheses, and we've seen these before in the substitution and the elimination chapter, and we've called them simply fill in the product or fill in the box around the arrow type questions. So there's really no difference here between giving a product to affect a certain change or calling them a one-step synthetic problem. And so we're going to consider them to be one-step synthesis problems with the goal of eventually being able to produce multi-step synthesis problems. And the way we would start practicing that is by coming up with one-step problems. So what we have to do is evaluate the reagent and the product and understand what is changing as we go from left to right. And of course, in this case, you can see that it's easy to tell that the alkene is disappearing and nothing else really exciting is happening. So all we're doing is taking the alkene and turning it into an alkane, and of course that is a hydrogenation reaction, and you can use your favorite metallic catalyst, palladium, platinum, or nickel, underneath the arrow, and we add H2. So all we're doing is adding H2 across this alkene. If we look at the second one, we again have an alkene, and we are adding the bromine now, and that's going to add to the more substituted carbon of that alkene. So we're adding a bromine to this carbon here, and that's basically our standard Markovnikov addition. And so really all we need to do is add HBr, and we remember the mechanism. The mechanism involves the formation of the more stable cation. That's this guy. Add bromine to that cation and we have our product. So really it's just HBr. There's no need to add anything else in this case. The third option here shows us this 7-carbon alkene, and then we have what sort of looks surprising. We have these two products here that are separate, and both of them have carbonyl functional groups. So this is a unique reaction that basically cleaves the alkene. So we need to do some cleavage, and that's going to be done with ozone and followed up with DMS as the workup here. So the first step is ozone, second step dimethyl sulfide. Remember that looks like this. And that reagent is used to ensure that we get aldehydes instead of carboxylic acids. So of course I didn't draw the hydrogen here. I could have had I drawn the OH here. That's a carboxylic acid, and that would be a different product, and that would require a different second reagent. That actually doesn't appear in our textbook, so we're not going to muddy the waters by introducing that. We're just going to use DMS. But understand that we could change the second reagent, and we could get a slightly different product outcome in that case. And the last one here is a ring with an alkene here. This looks kind of squiggly. That's supposed to be a straight line. And what we're ending up with is taking that alkene and turning it into a diol here. And it's important to recognize that this is an anti-diol. We could also make a syn-diol, and that would require a different set of reagents. And in order to make an anti-diol, we need to go through some sort of triangular intermediate. And we learned about that. This is what it's going to look like. And we hit it with water, and we can ring open like that. So this is a epoxide formation and then ring opening reaction. So the first step is some peracid. We can use peracetic acid. You could use MCPBA, or you could even just put R right there. And the second step is basically work up in acid to provide the extra hydrogen right here, and then it provides our nucleophile. And actually I think I should draw this a little more clearly, just so we're all on the same page with the mechanism here. These groups down here don't really play a role, they're just there as distractors. So the water attacks the more substituted carbon with the idea that that's going to have the greater partial positive charge. So that's where we get the anti-stereochemistry from. We're sort of doing backside attack on this more substituted carbon, and that gets us the anti-stereochemistry here. And of course, we could put our epoxide on the other side of the alkene, draw two dashes right here, and attack with the water from above, and that would give us this one. That would be the second option. The arrows that I drew here would give us this rightmost product. But you can see that I've still have anti-relationship in these products. I've retained the stereochemical information here. This is not affected by the reaction. And so if I asked you to come up with a relationship between these two products, hopefully you'll tell me that they are diastereomers. Right? We have inversion happening at these two carbons, which are basically the carbons of interest, and they participate in the reaction. And we have retention happening at this this stereocenter. And so that gives us several different stereocenters, but not all are different, right? This arrowed one is the same. And so we have a set of diastereomers here. So that's just something to keep in mind if you observe an existing stereocenter, and you can understand that it's not going to participate in our reaction.